Wireless communications has pervaded our daily lives. It has totally changed the way we work, the way we learn, the way we do business, and the way we communicate. Over the years, we have developed a number of consecutive generations of mobile systems, and historically speaking, the first generation systems was right across the globe based on analog technology. In the 1980s, the European Community's member states got together and developed the first ever digital mobile radio system, which became so incredibly successful that it was rolled out in about 150 countries right across the globe. And really its endearing feature was that it provided international roaming. In the meantime, we rolled out the third generation and the fourth generation systems as well, and so the systems coexist, and we refer to these systems as heterogeneous networks, in particular because there's a large variety of cell sizes, large variety of technologies coexisting, and at the time of writing, there's a tremendous momentum in cooperative communications as well, which really relies on the nodes communicating to each other in the interest of achieving a common goal, namely improving each other's communications quality. Of course, as the number of nodes is increased, the potential routes also proliferate, and so this leads to the classic traveling salesman problem, but of course the complexity of finding the optimum route is increasing exponentially. And so in this context, a number of different performance criteria have to be taken into account. In this example, I would like to just highlight two of those important factors, namely the delay as well as the power dissipation. So if we, for example, follow the upper route in the illustration, then there are 3 hops between the source and the destination, whereas in the lower route there is only 2 hops. The difference between these options is that the upper trace potentially has a higher delay because the nodes also have to delay their transmissions, so this is really more applicable to delay tolerant services. However, the benefit is that the hops become shorter and therefore the path loss is reduced, and overall the sum of the 3 path loss hops is actually potentially lower than the total path loss in the lower trace of the illustration. So by contrast, in the lower trace there's only 2 hops and therefore the delay is reduced, but again the power consumption or dissipation is increased. There are of course lots of other factors playing an important role in optimizing heterogeneous networks, and we at Southampton Wireless have had a lot of fun over the years optimizing these systems. For example, with the aid of genetic algorithms and colonies and various other weird and wonderful bio-inspired algorithms such as differential evolution and particles forming and so on. It's also worth mentioning that our goal is therefore to jointly optimize these parameters, but these multi-component objective functions are notoriously difficult to optimize. Let's exemplify, for example, in this illustration on the vertical axis, the delay, and on the horizontal axis, the power dissipation. The delay associated with this particular solution in the top left-hand corner can only be improved at the cost of ever-increasing power dissipation. And so if we connect these points, we arrive at what is referred to in multi-objective optimization as the Pareto front. And our goal is to find solutions as close to the Pareto front as possible. So this large-scale optimization problem, as I mentioned, can be solved with the aid of reduced complexity bio-inspired algorithms. Typically, full search is unrealistic. So allow me to briefly introduce the weird and wonderful world of quantum-assisted solutions. But perhaps taking a little step back first in history, in 1965, Gordon Moore, the author of the famous Moore's Law, was preparing a presentation and evaluating the trends in the microelectronics industry, observing that every 18 months or so, the integration density could be doubled. Now, remarkably, this trend has continued over the years, in fact over several decades, but it's set to finish in the classical world in the year 2017, and the traveler enters the wonderful world of quantum physics. In the community, the research efforts have been following perhaps a three-pronged effort. First of all, looking at the implementation of parallel computers and quantum electronics as such. The second is working on quantum information theoretic problems and trying to conceive solutions operating in the quantum domain. And thirdly, the solutions that we are also relying on in this particular treatise, namely the conception of powerful quantum search algorithms. The first quantum search algorithm in the literature was Grover's algorithm, which was capable of finding in a search space of n solutions, the solution with the aid of as few as square root n cost function evaluations. But this algorithm also had a disadvantage because it had to know the desired entry, and it also had to know the number of solutions in the search space. So by no means it's perfect, and therefore over the years several algorithms have been developed in order to be able to dispense with these limitations, amongst others the Dürr-Hoyer algorithm, which indeed succeeded in relinquishing these impediments exhibited by Grover's search algorithm. So in the paper, we will solve a triple objective optimization problem where we jointly optimize the delay, the power dissipation, and the bit error ratio. Wishing you intellectual fun reading the paper. Now, before I entertain you with the demo, I'd like to take you through some of the details in a static manner. So looking at the slide here in front of us, we're considering a relatively low complexity 7-node wireless multi-hop network topology with a source and a destination. Now, between the source and the destination, there's a whole multiplicity of potential routes, and we will be looking for the Pareto optimal routes. The paper looks at the three-component optimization of jointly optimizing the total power dissipation, the bit error ratio, as well as the delay. And I introduced the Pareto optimal concept with the aid of the delay and the power dissipation. So let's now move on beyond that and consider the bit error ratio versus the power dissipation in terms of the optimum Pareto front. And there are three different routes highlighted in the top left-hand corner, corresponding to the three different Pareto optimal solutions. So again, the Pareto optimum solutions imply that we cannot improve one metric without actually degrading one or both of the other metrics. Now looking at the rest of the slide here, we've got the interference power levels, which is indicated in this orange color, and at the bottom left corner we've got the Pareto optimal route list moving from the top towards the bottom, the top one being the preferred and with a decreasing order of preference, whereas in the bottom right hand corner we have the cumulative complexity graph corresponding to the brute force method, as well as the non-dominated quantum optimization and the non-dominated quantum iterative optimization algorithm. So altogether, we've looked at the various pictures that we will be looking at in the live demo, and so let's now move on to considering the live demo in a little more detail. Now, as the nodes move around, of course, there is always a Pareto optimum solution, and what we witness here is, I stop for a moment perhaps and take you through the different routes here. So the source node hops to the mobile relay number 5, mobile relay 3, mobile relay 2, and finally to the destination. And in this scenario, we can observe two Pareto optimum solutions. The other one being where instead of jumping through mobile relay 5, the message is sent directly to mobile relay 3. And what is worth observing, that the solutions are literally identical to the brute force method, which of course has a much higher complexity. It can be observed down here at the bottom right corner. So the blue line indicates the brute force method, the red line is the non-dominated quantum optimization algorithm, and finally the best solution in terms of the number of dominance computations or comparisons is represented by the iterative version of this non-dominated quantum optimization scheme, and it's denoted by the green curve. So as the simulation progresses, we will be able to see how the number of dominance comparisons increases, but the relationship remains the same in terms of complexity. So what is also perhaps worth thinking about for a moment, it is quite likely that the route here, which is the source node to mobile relay 5, 3, 2 and destination, in other words the node indicated here by the cursor, is likely to have a somewhat lower power consumption. However, it has a potentially higher delay because there is some buffering at the relay nodes. So again, it's another manifestation of the sheer fact that we cannot actually improve any of the features without degrading some of the other features. It's also quite interesting to observe that the bit error ratio is about 10 to the power minus 5 for both of these solutions. However, the power consumption is actually rather different. It's 66 dB here and 70 dB for the second solution. Right. So let me get going again a little bit with the simulations, and perhaps we observe a second interesting scenario. I wait until there is perhaps a multiplicity of routes. I will carry on still here because I would like to catch 3 routes, and I succeeded in doing that now. So we've got the yellow, the blue, and the green lines indicating the different routes, and these correspond to the 3 different Pareto optimum solutions. And again, there is quite a large difference in terms of the bit error ratio, almost an order of magnitude between the best and worst bit error ratio solution. But interestingly, the power difference is relatively small between them. So looking at the list of the different Pareto optimum routes, the green route, the source node, mobile relay 5, mobile relay 3, 2 and destination is potentially the most preferred one, and moving down again we can see that the 3 solutions here are associated with literally the same performance as the brute force method, but down here at the bottom right corner we can see that the brute force method has a substantially higher number of dominance comparisons. So let's carry on again a little longer. There are sometimes even a higher number of Pareto optimum solutions. In this situation I managed to capture actually 5 of them, but again actually the bit error ratio is relatively high. So quite clearly this would dominate the overall performance of this network, because when we compare the 10 to the power minus 5 scenario to the 10 to the power minus 3, then the 10 to the power minus 5 could be considered almost error-free. So moving on, I now let the demo to go through perhaps all the way to the end, and then I will let you play with the demo yourself and experience the operation at its best. Perhaps just mentioning here that this lilac colored scenario is deserving some special attention, but again I'd like to leave that for your exploration.